Last time we started talking in this section about volume, we looked at volume conversions within our metric system and within our standard English system. And we had gotten to the point where we were going to look at a few formulas for some different shapes and how we would find volume of these specific shapes. So that's where we'll pick it up. All right. These formulas are usually a little easier to calculate than the surface area formulas. There's fewer steps involved. The first one is actually the right rectangular prism, like the last example problem we were looking at from the homework. And to find the volume of the right rectangular prism, we would take the length times the width times the height. No adding things in. That's what makes this usually a one-step process and a little bit easier to compute. If you have a right, or an oblique prism, and you've got the shapes here, yours are beside each other on your paper, what you do is you take the volume to be the area of the base, that's what we've been calling capital B, times the height. So if you have a rectangle base, you find the area of the rectangle. If you have a triangle base, you find the area of the triangle. And then no matter whether the shape is right, as in straight up and down, or leaning, like oblique, you find the height. That's the perpendicular distance from top to bottom, and you multiply by that height. So simply taking an object and leaning it over does not change its volume. It changes its shape and how it looks, but it doesn't change its actual volume capacity. To parallel that, we have our cylinders. And with our cylinders, we will have the R is the radius, H is the height. And so then the volume of a cylinder is much like this over here, actually. So what did we do? We took the base, the volume of the area of the base, and times the height. Well, the area of a circle is pi r squared, and then we multiply again by the height. So it's actually the same formula over here. It's just that we know it's a circle on the bottom, so I can fill in a formula for the area of a circle, whereas over here it could be any shape along the bottom, and it would work. So that's for a right circular cylinder. For a cylinder in general, it's much the same. In fact, the formula looks just like the one on the previous slide. We take the area of the base times the height. And you might be looking at that and saying, yeah, but if it's a circle base, won't you have the same formula? And the answer is yes. But remember, cylinders don't have to have bases that are circles. What other shapes could be on the base of something that we would call a cylinder? What's that? An oval. That's probably the most common one we would think of. I think that I gave you guys an example, I've used it in the past on our first exam, of a shape that actually looks like a heart on the base. I may not have done this, I totally may be lying to you, but I've done it in the past and done a heart up here. And if I drew it right, it could also be a non-circular cylinder. There's nothing wrong with that shape, okay? So the cylinder could have that shape. It could have anything, actually, but this gives us more flexibility, so we could have some other type of shape on the bottom, but we find the area of the base and then multiply the height just like we would if we found the area of the circle on the bottom and multiplied by the height. All right, so cylinders are very similar in their formulas to prisms. Okay, that's why these are sort of grouped together. The other two that are very similar are cones and pyramids. So when we have a pyramid, its volume is much like the other ones. It's base times height, but of course it's not as much volume, right? I mean, it's narrowing down to the apex instead, or up to the apex either way. It's not got these same, they're triangles on the sides. They're not rectangles. There's got to be less going on. It is. It's actually 1/3 of the base times the height. So the formula is very similar. You just have a 1/3 factor to it. And then your right circular cone looks a lot like the circular cylinder, but again, and again, I should say, if it was an oval base, we could write it much like we could do just the 1/3 base height. But we have our pi r squared times the height. That's the same as we got for our cylinder. And we have a 1/3, just like we did for our pyramid, as compared to our cylinder, or our prism. So it's still pi r squared h. It's just 1/3 of that. And our last shape that doesn't sort of fit in those two categories is a sphere. And the volume for a sphere is actually 4/3 pi r cubed. And when we get to Thursday, we'll talk about what do I need to have on my note card or memorized versus what am I going to give you for the test. We'll address all of that later. So for right now, let's just keep moving, but we will talk about those things, okay? All right, so we're going to do some examples of some of these shapes and finding their volume. This one says to find the volume of the ice cream cone. So that's of the entire picture image that you see here. How could you break this down into two different objects that we could find the volume of? What do you see? A cone and a what? And the hemisphere. And we've done this for surface area before. It works much the same way. So the formula for the volume of a cone is 1/3 pi r squared h. A hemisphere is 4/3 pi r squared. Pi r cubed. Did I write it right on the right screen? I did, okay. That's pi r cubed. And then what do I do to get a hemisphere? Because that's the surface area, or the volume for a sphere. Over 2 or times 1/2, either way. Since I already have a fraction here, I'm going to put it times 1/2 because it feels funny to me always to see fractions over fractions, and so it's a little bit cleaner. And we're going to simplify this, okay? So we have some numbers given to us. We are told the radius of our cone. We are told the height of our cone. And I think that's all the information we need for either of those volume formulas. So we have our 1/3 pi. The radius is 4, so it's 4 squared, and then our height is 8, plus, either here or later, we're going to multiply this out. So this is 4 times 1 is 4, 2 times 3 in the bottom is 6. Reduce it if you want, or later, I don't care, but it's a 4/6 or a 2/3. And then I have, pi, and then r again, which is 4 cubed. Now, there are units. This has context. You're welcome to grab your calculator and to use approximations with that. 2 decimals of accuracy is plenty for us. If we simplify this out with numerical values and clean everything up, let me just tell you what it works out to being. You don't have to do that part of it for me, but it would end up being 256 pi over 3 if we cleaned it up properly. Cubic centimeters. Decimals are fine though. So what does your calculator give you when you simplify the expression in the calculator? Did you get it, Allison? No, not yet. Jillian, what do you have? 268.08. Fantastic. Does anyone else get that? That's what's on my paper. So like Sabrina and Tori said, okay, good. So this would be our contextual kind of answer. 268.08 cubic centimeters. All right, we'll do a couple more. This is the volume of a right triangular prism. So what was the volume formula for a prism? Yeah, capital B, which is the area of the base, times the height. All right, so I think in this picture we first need to look at it and imagine for us where our bases are and where the height would be. So where are the bases? What are they shaped as in this picture? Are they the rectangles or are they the triangles? They're the triangles. So the triangles are our bases here. So then what does that make the height? It's what? 12, correct, good. So we actually need to find the area of this base then and put it in. So if you want to do it as sort of a separate piece of the problem and then plug it in, you can. If you want to just fill it in right here as we go, you can. It's your choice. But we need the area of the base, and the base is a triangle. What is the area formula for a triangle? 1/2 base times height, but please be careful. It's the height of the triangle, not the height of the pyramid or the prism or the whatever else we're working with. It's the two-dimensional shape. that we have as a triangle. So in this picture, what is the height of this triangle? 6. And what is the base of this triangle? 6. They're both 6. So it looks something like this. So if you multiply 1/2 times 6 times 6 times 12, what will you have? And 216 what? Right, cubic centimeters. Okay, let's take a look at our last example of these, which is about a straw. We have a standard straight drinking saw. That's important because there's bendy ones and things like that too, right? And it's 25 centimeters long, 4 millimeters in diameter. How much liquid can be held in the straw at one time? Have you guys ever played the game where you have to fill the straws up and you have to move it from one bucket to the other and you're trying to, this is important information if you're playing that game, right? You would want to know. And actually, if you were coordinating this game, you would also want to know because it might make a difference on where you drew the line that the children had to fill it up to. You make that game last too long and everybody's going to be like staring at you like, I'm done, I'm not playing this game anymore. And this is a personal experience story because my husband did that once. He put the little line a little too high and he lost the interest of all of the students who were playing it. It didn't work. All right, so let's start by drawing a picture of our straw. And we'll make it a little bit exaggerated because it'll be easier to put all of our details in. So this is not drawn to scale by any stretch of the imagination, okay? Here's my straw, something like this. It tells us that it's 25 centimeters long and it's 4 millimeters in diameter. So does anybody see a concern already? The units don't match. So please be aware, pay attention to that. The units need to match in order to continue the problem. So now you have to decide, do you want to use millimeters or do you want to use centimeters? And there's not a right or a wrong answer, but we do need to decide, and let's decide together. Centimeters? Millimeters? I think I heard centimeters mostly. Are you guys good with that? Okay, so if we're going to go with centimeters, the 25 is going to stay put. And the 4 is going to change to what? What would 4 be in centimeters? 0.4. So I've got 0.4 centimeters for my diameter. All right. So then, what is the volume formula for a cylinder? Because that's what the shape is. Pi r squared times the height. Well, I've got the height. That's 25. What's r? 0.2. So remember, the diameter is what's given to me. The radius is what's actually needed in the calculation. So our radius in centimeters would be 0.2, and then I'd have that squared. And then my height's 25. Now, you got to show me something where you're filling in all the numbers. All right, so this step, absolutely crucial. You got to show me what you're putting where. As much as for your own protection as for my benefit, because then that means I can give you extra or partial credit if there's something that just flat out doesn't translate into your calculator right. I can know you were on the right track, okay? What do you get for this as an approximation with 2 decimals? What? That's what pi is.
Yeah.
But then did you multiply the 0.2 squared and the 25?
That's what I got too. 3.14159. Because 0.2 squared is 0.04, and that times 25 is 1. So it is 3.14.
Okay, I just have an error, I guess, written down on my paper then. So you got 3 point what? So 14 if we're doing 2 decimals. 3.14 what? What are your units?
That's in centimeters.
Cubed. It's volume. Yeah, cubic centimeters. Okay, cool. Any questions on that? Alrighty. So we're going to have a little discussion about mass versus weight. Mass is actually the amount of matter in an object, and weight is how much force gravity exerts on an object. So weight changes when the amount of gravity changes, but mass is not affected by gravity. So if you've ever been somewhere that they have a scale where you can ask it, how much do I weigh on the moon? You guys experienced that before. The Science Museum has one, but there's other places that do too. That's what this is getting at. The gravity on the moon is different than the gravity on Earth, so your weight is different. However, your mass is the same. You don't actually become skinnier on the moon. It's a sad reality. Just the number on the scale changes. I know, right? We should all move to the moon and become skinnier. The English units for weight include the pound, the ounce, and the English ton. An English ton, and I'm using the word English because there's another kind of ton. An English ton is 2,000 pounds. Sometimes you'll see these on bridges where they'll tell you the weight that the bridge can support, and think in terms of like large trucks, semis, stuff like that, and they'll write it in tons. So if it says it's a 5-ton bridge, now you know you can take 5 times 2,000, you know the weight of the truck that it's telling you can be on that bridge. Metric units for mass are actually based on the gram. If I have that over on the next slide. Oh, yeah, there we go. And the conversions are the values that we've seen before. They're coming up again in our notes here too. We have the gram, the decigram, the centigram, the milligram, and so forth. The ones that are starred are the ones that occur that we actually use. Okay, they all exist. It's just they're the ones people record values in: milligrams, grams, and kilograms. And this is what you did in your activity at the front. You know, when you were looking at mg, milligrams, or kilogram. Or we didn't have. I don't think we had any with kilograms actually on objects, but we talked about it. And then we have metric tons. So if it weren't bad enough, we now have English tons and we have metric tons, and they're not the same thing. So that's super helpful, right? Call it something that's the same, but it's not. A metric ton symbol is just a T, a lowercase t, and 1,000, its equivalency is 1,000 kilograms or 1 million grams. Okay, so still got that base 10 conversion thing going on for us. But it's going to be just like when you go from grams to kilograms, you multiply by 1,000. If you go from kilograms to metric tons, you multiply by 1,000. That's the deal, okay? It's a 1,000 conversion. All right, so some capacity measurements for water. So just like we looked at last time, there's these conversions that take what look like linear measurements into milliliters. They also can take them into gram measurements. So 1 cubic centimeter is equal to 1 milliliter. We did that last time. And it's also equal to 1 gram of water. So if you're pouring milk, this doesn't apply. There's a different density involved, right? You guys know that some of the things you drink are thicker than others, right? So this is all based on water measurements. 1 decimeter is the same thing as 1 liter. 1 cubic decimeter is the same thing as 1 liter, which is the same thing as 1 kilogram. Okay, so we're going to do a couple of 3 maybe conversion questions on this. So this wants us to convert 30,689 grams into metric tons. So what is the conversion for grams to tons? It's 1 million. Now, if you're really good and you recognize how many places it needs to move decimal places, that's wonderful. It's 6 is the actual answer. If you weren't sure, because this is one of our standard like King Henry died ones, I mean like that one, then you can actually set up your dimensional analysis like we've done before with the fence, and you can do it from that way. So Alicia told us it's 1 million, which is correct. So 1 million grams, and this would be equal to 1 ton, and that's a T in metric. So you could actually take your calculator and you could do this division. 3689 divided by 1 million, and what do you get?
0.003689.
Metric tons. Okay? So we're going to complete the following relationships. 1 cubic meter of water has a capacity of 1 what? So let me walk you through how this works. We know we've got a cubic meter, and our cubic meter would be 1,000 decimeters. If you'll remember to go, let me write it at the top. If you're going from meters, which is here, to decimeters over to the right one, right, D, then it's 10. It's a factor of 10. And we're cubing things because we've got cubic measurements, so 10 cubed is 1,000. It's a 1 with 3 zeros from the 3 tens. But what are decimeter cubed? What is the cubic decimeter to kilograms? It's actually 1, right? 1 cubic decimeter is the same thing as 1 kilograms. So how much would 1,000 cubic decimeters be? It would be 1,000 kilograms. Okay, well, but that's not number 1. I'm supposed to be filling in the blank with whatever it equals in the value of 1. So let's go looking for a conversion that is what 1,000 kilograms would be. Well, capacities in terms of liters. Did I go too far? Well, that'll work, right? There's 1 liter right here, correct? Capacity is measured in liters. So we could go from kilograms into liters. We could do that. So instead of going into 1,000 kilograms, maybe we should have gone into 1,000 liters. That would have been a little bit more of a direct step, right? Because it was along the same line. 1 decimeter cubed is 1 liter. And then what can I do to change this into a measurement in liters? Liters is capacity, right? That's why we're trying to get to liters. What would how do I get this to be 1 something? What is it? What type of liters? It'd be kiloliters. I need to move from, move it back up here, the base unit over to kiloliters in order to get the conversion factors. This is 1 kiloliter. All right, let's do this next one. It's 1 cubic meter of water. So again, all of our measurements are converting things into liters. That's where our goal is. So 1 cubic meter, which we just did before, was 1,000 cubic decimeters. Oh, it's not, I'm sorry, it said mass here. I was looking at the line before, has mass. So now we need to go into mass. So if I look at the conversion for decimeters into mass, mass would be kilograms, right? Last time I did liters because it was capacity. This time I'm doing grams because it is mass. And so I would have how many kilograms? 1,000. These are all 1-to-1 ratios on this particular chart. That's a very friendly chart, actually. This is equal to 1, equal to 1, equal to 1. But what is the, what is the mass measurement that would be 1,000 kilograms? 1 metric ton. You got it. So this is 1 T, or metric ton. Lovely. All right, let's do an actual application problem with volume now, because we've done some examples of sort of some visuals here. This one was a nice application one. Let's do one more of those. We have an Olympic-sized pool in the shape of a right rectangular prism. It's 50 meters by 25 meters, and it's 2 meters deep throughout. Okay, so this is not the pool in your backyard that has the sloping, deep end and shallow end. It's all level. It wants to know how many liters of water does it hold. So if it helps you draw a picture, then fabulous, draw a picture. I will draw one real quick. So this is sort of the image that I have going on here. This is terrible. I needed it to be the same length. That's what happens when I freehand. I don't draw well. That's not too bad. So it says that the size and the shape of it from sort of the top view is it's 50 by 25. So I think that's 50 here and 25 here, sort of perspective-wise. And then it's 2 meters deep throughout. So what in the world would I do to find the volume of my pool? Yeah, length times width times height. 50 times 25 times 2. What would that give me? Close. I think it's 2,500. You're off by one decimal place. 2,500 what? Meters cubed, which isn't exactly a liquid measurement. Like, we don't think about that, right? So our liquid measurement would be the same as capacity or liters. I need to turn this into liters. So I have a way to do that over here. I have that 1 decimeter cubed is the same as 1 liter. I don't have this in decimeters though. So I need to get 2,500 into decimeters. How did I do that multiple times over here? What was the conversion? Yeah, I pretty much put 3 zeros on there. I multiplied by 1,000 is what I did. So this would be 2,500, and then, like Alicia said, we need to have 3 additional zeros on there. So we actually have 2,500,000 decimeters cubed.
I'm sorry, I don't understand why you multiply.
Okay, so we're trying to go from meters into decimeters. So meters is right here. Oops, I meant to do that in a different color. It was right here. And then decimeters means to do 1 more 0. But we're going to do it 3 times because we're doing cubic decimeters. So we get 3 additional zeros. But how are the cubic decimeters related to liters? What kind of relationship do they have? It's a 1-to-1 correspondence, right? 1 cubic decimeter is 1 liter. So 2.5 million cubic decimeters would be 2.5 million liters. So this is 2,500,000 liters of water. So you're not going to fill it up with the 2-liter bottle or the bucket or something like that, right? Huge. Huge, huge number of liters. Okay, the last kind of piece in this section is about temperature. So we've talked briefly, as in you've received a worksheet where you thought a little bit about temperature. We're going to talk a little bit more about it today. The base English unit for temperature is the degree Fahrenheit, which you know. The Fahrenheit scale divides the temperature range from freezing at 32 degrees to boiling at 212, and it divides it into 180 equal parts. We're all comfortable with it. If I tell you it's 70 outside, you don't ask me, Celsius or Fahrenheit, Dr. Hands. We don't even think like that. This is the system that we're accustomed to. We've grown up with it. All right? So we like it because it feels good to us. We know what we're talking about. However, it doesn't have the beautiful features that the metric system actually has. So the metric system scale is the degree Celsius scale. It actually has freezing water. Water's freezing point is 0 degrees Celsius, and boiling is 100 degrees Celsius, and then it divides it into 100 equal parts. It's very friendly. Everything's, again, based on that, metric system with the number 10, base 10 stuff. There's actually a third unit of measure called the Kelvin, or way of measuring temperature called the Kelvin scale. Primarily used in science. You maybe have heard about it in some of your science classes for scientific measurements. The Kelvin scale is simply an adjustment of the Celsius scale so that there is an absolute 0. So the absolute 0 on there is actually the coldest possible. So like we all recognize that it's possible to be colder than freezing, right? So whether you think if freezing is 32, you know you've had temperatures below 32. If you think in terms of Celsius, freezing is 0, you know you can have negative Celsius degrees. There's no negative Kelvin. 0 Kelvin is absolute 0. Like there's no colder temperature beyond that. It's actually 273.15 degrees below what our 0 would be. Crazy stuff. So 273.15 in Kelvin is 0 degrees Celsius. And add 100 on, we'd be at boiling point. I don't know about you, but I don't want to experience 273.15 negative Celsius. That does not sound good. But that's the conversion for those. All right, so taking a look, here is kind of a scale. If it were me, I would use some modified version of this scale as I'm thinking through things on my note card, or make sure that I sort of have this picture in my mind. This is a fantastic image. No, you can't copy and paste like an actual piece of this onto your note card, but you can rewrite it if you'd like. This actually shows you the comparison from the right-hand side to the left-hand side. So you have our body temperature on there, 98.6 is about 37 Celsius. You've got room temperatures marked on there and other facts. Okay, so this gives you some perspective. And we're going to do two examples about conversion, one example and after the formulas, but I'm going to show you the actual conversions between the two. So prior to now, all I was asking that you had a ballpark idea of some of these values from the worksheet we did, but I'm actually going to show you how we convert. So converting back and forth between these scales looks like this. So Celsius is 5/9, Fahrenheit minus 32. And likewise, Fahrenheit, if we just undo this and resolve it, would be 9/5, so it reverses it, Celsius plus 32. Notice, the first formula, you subtract the 32 first. In the second formula, you add the 32 last. Those parentheses and order of operations make a difference. So make sure if you're using one, you know which ones, so to speak, got the parentheses and which one doesn't. So our last example for this whole semester together in this format is what in the world would 40 degrees Celsius be in Fahrenheit? So looking at that, you can actually pick which formula you like to use, but one's a little bit more direct than the other one. Which one would be the most direct formula to use? The second one. So I have Fahrenheit equals 9/5, Celsius plus 32. This is the most direct one because it's going to have me put things in and get Fahrenheit out, F equals. So here's 9/5. Notice we're going to do the multiplication part first and add the 32 last. And if we do, what temperature do we get? 104 degrees Fahrenheit. Why is that an important temperature in the lives of many adult peoples? I don't want to give it away by giving more information than just that. Has to do with fevers, right? So almost said adult women, but I don't want to exclude the men. This is an important number they should know too. And being is that you're going to be a teacher, it's important to you because you're going to be with kids. Many of you at some point will probably be a parent, and it becomes an important number to matter when you're looking with kids. If we feel awful, we just know we need to go to the doctor. We don't really care what the temperature is. But if our kid is not feeling well, these are important numbers to know. A temperature above 104 is emergency situation, so that's why it matters. So if you were working in a temperature or in a situation where Celsius was more commonly used, maybe you are teaching overseas and the thermometer says 40, you know that's an important number for you. 40 degrees Celsius for a child's temperature is a problem. But notice over here, what is the normal temperature for a child or person to have? 37, right? So those numbers sound really close, but actually they make a difference. Does that make sense? Awesome.